Alright, we are back. This is Techmath2. We're looking at 614. So let's take a look. Evaluating formulas containing powers. So I had a calc teacher in college that would refer to these type of problems as plug and chug. You just plug in the numbers and chug out the answer mathematically. If you want the fancy words, it would be substitute in for the variables and evaluate using order of operations. Alright, but plug and chug sounds like more fun. So here, S is 13.9, T is 47.6, and we're going to divide that and then raise it to the 0.1 power. Although you have calculators that can handle order of operations, you just do a parenthesis 13.9 divided by 47.6 and parenthesis caret 0.1. So it actually looks like this. You have to put that division in parentheses though. So that otherwise the calculator will follow order of operations. If I don't have those parentheses, it'll evaluate the 47.6 to the 0.1 power and then divide it, and that will give you the wrong answer because that's not what the formula states. All right? So parenthesis 13.9 divided by 47.6 and parenthesis raised caret to the 0.1 power. And we're looking at 0.884 dot 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 dot. So how many decimal places do they want? Thousandths. So tenths, hundredths, thousandths, 3 places, so 0.844. And then there's or 0.884, sorry, 0.884. 0.884, and so there's a 1 after it, so it just stays that. 0.884. All right. Okay, let's look at the next one. Oh, you probably used both of these at one time. That's like the interest. In Techmath2, we definitely used the interest. So we had principal, $1,000. Interest rate is 8.5%, but they already have it at a decimal already even. And then we raised that to the 10th power. That would be n number of years, simple interest. So again, you can type that all in, 1,000 parenthesis 1 plus 0.085 and parenthesis raised to the power 10 and then hit enter. And that would be, after 10 years, $1,000 at 8.5% interest would be $2,260.98. Oh, wait, I made the assumption we were talking about money. Apparently we are, but they want it to a whole number, so. 2261. And same dog, different fleas here, 250. And 60 plus 1, so this is not the same type of formula. That's not interest. You can't, unless it's 60 would be 6,000%. That would be a pretty big percentage. All right, so let's see, 250, 61. I could just add that right in your head and paren to the 0.5 power. So that is 1952.5, so we'll call it 1953. Okie dokie. Lovely. So exponential functions, that's when exponential functions are when you have a number as a base and a variable as the exponent. It's called exponential, and there's exponential growth, there's exponential decay. So you see it in science all the time with exponential functions. And we'll take a quick look at just a graph. They don't really go in depth at this point. Again, I think in Techmath2 we did look at exponential growth and decay. So this should be just kind of a review. So exponential functions. Look at 148, so 615. They have a is equal to y, or rather a is y equals 3 to the x, b is xy equals 10, c is t equals 5 to the negative d, and d is y equals 14x squared. And they want to know which one of those are exponential functions. Well, to be an exponential function, it has to have a base, and then the variable has to be in the exponent. So this one is exponential, because the base is 3, and then the power is x, and so that would be an exponential growth, because if the number is bigger than 1, it's growing with each iteration. As you put in 1, 2, 3, 4, you'll get larger numbers. If this were between 0 and 1, like a fraction, then it would be exponential decay. That is not. That's just y equals 10 over x, so that's a parabola. It's x squared, but see, the variable is the base, and the power is just a number. So that is not exponential growth. Oh, this one is. We have a number base again, and even if it's to the negative d, if we wanted to transform that we could say it's like this, -1 raised to the d, so that's like 1/5 to the d, so it's actually exponential decay, but it's kind of tricky because they had the negative exponent on there. And so, at any rate, because even without that, if you just look at it, we have a number base and a variable in the exponent that makes it exponential. So, all right, 2 exponential functions there are a and c. And then let's look at 152 quick. They want us to graph it. And if you look at it, they already kind of have the graph there. It's y equals 2 to the negative x. So again, they're doing this. Remember what that means. That's y equals 1 over 2 to the x, because that negative sends it to the bottom. And then if I wanted to write it, I could say 1/2 to the x power, because then, you know, like that goes on the 1, that just would stay 1 no matter what, and that would go there, like 1 times x would be that. So it is exponential decay. And so what happens with exponential decay, that is 1/2 to each one of these powers. So you could put in -2 and -1 and 0 and 1 and 2. And so when I put in -2, that actually, you could go 0.5 to the -2 power, and check it out, that's going to be 4, right? And a -1, that's just going to move it up, that'll be 2. Anything to 0 power is 1. 1 is 1/2, 2 is 1/4, 3 would be 1/8. And so what's happening with this graph is it's exponential decay, meaning we're coming down and approaching the x-axis, but it'll never actually cross the x-axis. It'll get forever closer to it, but it'll never cross it. And so they have that graph on there too. So exponential growth, exponential decay. If that were a positive or a number bigger than 1, then it would have went like this and went up instead of down. Okay. So that is 6:15. Oh, and that concludes chapter 6.